All right. Hey there, everybody, out in the global Hack Week world. How are you today? I hope that you had a great rest of your day after we logged on last time from part two of this series. And hey, now we're going to start with part three. So um, I hope you all are excited. Yeah, let me actually get some of these slides ready because I want you to have those so that we can all go together on these problems. All right, there we go. Of course, we're not on part one anymore. We're now moving into part three. And DS0707 asks for a recap of part one and part two. That's great. I can totally give you that. Basically, we were doing some data structures and algorithms practice. So in the first part one, we did some data structures. I'm going to actually, I have a slide for a recap. Let me see if I can pull that up. Yeah, let's see here. It's slide 40. All right. Let's see. There it is. So these were a few of the different things we talked about in part one. And they were mostly to do with data structures. So we talked about arrays and strings, which are super efficient for having an indexed access to data. So it was basically having contiguous storage of data elements where, one element comes after the other after the other. We could traverse an array where we just go through all the elements in sequence. And we can know that they are fixed size, although sometimes in some languages, you might be able to add a new element to an array and increase its size. And then we also talked about linked lists, which have a dynamic size and are efficient in doing insertions and deletions. And so, you can think of a linked list as having two components. It's going to have data, which is stored in what we call a node. And that node will also have a reference or a pointer, which indicates what the next node will be, where the next data is stored. And so in that way, all of the nodes in the linked list are connected to each other, and that's why we call them linked. Okay, and then we did also have a data type called stacks and queues. So stacks are last in, first out behavior, where it's really useful for recursion and backtracking, and that's really great. And then queues are a little bit different, where you had first in, first out behavior, where you could use them for scheduling and sort of tracking buffers, things like that. And we actually built a queue out of two stacks that were connected to each other. And then finally, we talked about hash tables, which were basically fast data retrieval using keys. So we were actually going through and, learning about the hash tables a little bit too. And then let me show you what part two was about, because, we should definitely cover a recap of that too. So here's the recap of part two. We did some essential algorithms, so-called essential algorithms, like sorting algorithms, like bubble sort, selection sort, merge sort, and quick sort. So those were our four main sorting algorithms that we covered, and we learned that bubble sort and selection sort both operate on a time complexity of O(n) squared. So we talked about big O notation and how they're kind of slow in terms of sorting algorithms. And the two faster ones were merge sort and to some extent quick sort, where we split up the data first to actually then sort it in the end. So yeah, that was really great. And now we can talk about searching algorithms. So searching algorithms are where you know an element that you're looking for in an array, but you just don't know where it is. So you do a search. And a linear search is pretty slow, honestly. It's where you go from one element to the next and just go along in a linear fashion until you find the element. But the problem with linear search is that the element you're looking for could be at the very end of the list. And so in that case, you'll be spending a really long time looking for it. And binary search is where it then comes in, because you can split up the data first. And doing those splits, you're going to save a lot of time if the data is far in the list, because you can kind of make your way in that direction without having to check all the numbers first. But binary search is really important to remember. You need to have sorted algorithms, sorted lists, excuse me, in order to run it. So your array or your list needs to be sorted in order. And we don't always have that. So after we covered some essential algorithms like sorting and searching algorithms, then it was on to some of the design techniques that are used in developing some of these. And we covered greedy algorithms and divide and conquer, and even some intro to dynamic programming. And so that was part of what we did last time. And so, hi there, Gluonic Boom. I see you have a question. What is the right approach to master dynamic programming? So that's a great question. I actually, I think, we're going to cover a lot of dynamic programming today. So we're going to actually go into more detail about it. But I think I'll post the slide from last time. It's really about finding the optimal substructure, which is one of the key concepts we mentioned last time in part 2. It means that when you have a problem, always be thinking about, okay, in this problem, is there any sub-problem that I can find that I can then optimize? So just keep an eye out for problems where there might be two things going on at the same time, like a retrieval of some data and also a sorting, for example. We could optimize those separately. And we're going to go through a concrete example of dynamic programming when we do part 3. So I encourage you to stick around for the answer to that question. All right, so why don't we now move on to part 3? It's going to be really exciting. And before we do that, I want to make sure that you all check in for the event. So the check-in link is available here, also on Discord. And I even put the check-in link in the chat so that you'll have access to it. Definitely make sure to check in, because that's how we know what kinds of content you all are interested in seeing. Well, Hack Week, and it also helps you get some points for swag and things like that throughout the event. So I highly recommend to do that. All right. But welcome back for part 3. Let me just introduce myself briefly. I'm Stephen from MLH. I've been working with hackers for over 6 years now in Major League Hacking organization. And our reach has really grown over that time to now have, thousands and thousands of hackers around the world that we reach out to and work with. So it's great to be with you all today. And for this workshop, we have some goals, of course. We want to understand advanced data structures like trees, heaps, and graphs. We want to learn some algorithmic problem-solving strategies, and we're going to tackle two methods, which are dynamic programming and backtracking. And then we're going to apply those concepts through some interactive coding problems like we've been doing in our previous parts. But hi there, 404. Good to see you. I haven't seen you in a while. And yeah, I'm doing great. Actually, this time doing a lot of the Global Hack Week streams. I think I'll see you all even some more this week after we're finished with this track. We have 2 more tracks with me. Data visualization, we're going to cover some data visualization packages in Python, including Dash, which is dashboards in Plotly. We're going to cover some of Matplotlib as well. So we're really going to get into some of these great visualizations, interactive visualizations, animated visualizations together. But yeah, for now, these are our goals, and we can apply these concepts through interactive coding problems. So we'll do that. And, why do we study some of these more advanced topics? So, now that we've gotten our foundations, we can start going into more advanced topics to apply these foundations to efficiently solve complex problems. So most of the problems you see in computer science, in your day job, let's say, they're not going to be, hey, I have an unordered list of integers. Can you please sort the unordered list of integers? But they might ask you to sort some data, read some new data, things like that. So you're going to want to know some of these concepts in order to solve the problem. And we'll also need to improve our coding skills for real-world applications and prepare for challenging technical interviews because, believe it or not, a lot of these concepts will show up on some technical interviews that people will want to give you for some kind of software engineering job. So yeah, with all that in mind, let's go ahead and get started. And Akshat has a question from yesterday, so please feel free to ask that. I'm happy to go back to yesterday's materials. We should have enough time to do that. And if you have a question from part 1, that's totally okay too. But yeah, let's keep going. So trees is the next thing we have. So trees are composed of some key elements. There's the root node, which could be a top node with no parent. And then there's the leaf node, which is a node with no children. And there's internal node, which is a node with at least one child. And there's the edge, which is the connection between 2 nodes. And there's the tree, subtree, excuse me, which is a tree consisting of a node and its descendants. And so, yeah, these are the different ones. And oh, I have a question in the chat. Yes, what algorithm does sort use? So sort in Python actually uses a hybrid sorting algorithm because think about it. In a lot of cases, you might want to use one type of algorithm for certain applications, but another one for others. So the fastest algorithms are usually merge sort. So it probably uses merge sort, but it probably isn't as simple as that because there might be some applications where another algorithm is faster. So it's probably what we call a hybrid sort. I'm going to put that in the chat. The hybrid sorting algorithm, where you might look at the data first to see what will be the best algorithm to use to apply to this data. So that's a good question, Akshat. And oh, thank you, Gluon, for the kind words. Yeah, we try to keep the vibe super positive here in the Global Hack Week. So yeah, definitely thank you for the compliment. And yeah, we'll keep going now with binary trees, which is one particular type of tree data structure. And it's the one that we're going to talk about probably the most for now. So a binary tree is a tree where each node has at most 2 children, and those children are referred to as the left child and the right child. Could you imagine if imagine if you had 2 children and you named them left and right? That wouldn't be very nice. Well, maybe somebody named their children left and right, but in computer science, that's what we call our children, left child and right child. And the types of binary trees that we could have are many. So there's full binary trees where every node has 0 or 2 children. So what that means is that every node is having 2 choices until it hits the end, right? A terminal node where there's no children. But you don't have to be a full binary tree in order to be a binary tree, because each node has to have at most 2 children. So there could be cases where a node has 1 child, and that would still be considered a binary tree. And then complete binary tree is the case where all levels are completely filled, except possibly the last level, which is filled from left to right. So that is a case where all levels get populated with these two children. And then perfect binary trees are ones where all internal nodes have 2 children and all leaves are at the same level. So we'll actually investigate a binary tree here. Here's a binary tree. I've given you an example. And so I want you all to take a look at this. I'm going to give you a few minutes to think about it. Is this binary tree any of the special trees that we've talked about? Give you a minute to think about that. All right, so just to give you the answer here, a full binary tree is one where, remember, each node has either 0 or 2 children. So can any of you see a node which does not have either 0 or 2 children? All right, so I actually don't see any node which has less than 2 children or 0 children. So, actually, I think this might be a full binary tree. Now that I think about it again, so that would be a full binary tree. But is it a complete binary tree, would you say? Because remember our definition of complete binary tree. All levels are completely filled, except possibly the last level, which is filled from left to right. And so I don't think the nodes are being filled in the left to right order, because if you look over here at the beginning, the left node here doesn't have any children. So we would not say complete binary tree. So full binary tree, we could definitely say yes, but complete binary tree, I'm not so sure. And then perfect binary tree is a tree that has all internal nodes with exactly 2 children and all leaves at the same depth. So if you look at this binary tree that we have, it definitely doesn't have leaves at all at the same depth. There are some leaves that end at the first level, there are some that end in the second, and some even in the third. So I would say this is a full binary tree, but it's definitely not a complete binary tree or a perfect binary tree. There's one last one we could have, which is called irregular binary tree, which if it doesn't fit any of these, then it's irregular. But yeah, so hi there, Adele. So it's good to see you. You did not miss too much. We were just talking about binary trees. We spent most of this beginning period recapping from the first 2 parts of the course. But now we're looking at binary trees, and just to give you everybody a refresher here, it's a type of tree which has at most 2 children. And so we were seeing if this binary tree we have in this picture is a special one, meaning full binary tree, complete binary tree, or perfect binary tree. And we did see that it was a full binary tree because, as you can tell, every node has 0 or 2 children. I couldn't find any nodes here that have just 1 child. But yeah, so there's our binary tree example. Oh, I don't know why I have a blank slide here. Maybe I just left that in on accident. Let's skip it. But yeah, now let's talk about tree traversals. So we did talk last time about arrays and traversals in the context of an array. And does anybody remember what the array traversal meant? What did it mean to traverse an array? Anybody remember that? We did talk about it in part 1 of the workshop, about what it would mean to traverse an array. Yeah, so just to give you the answer here, oh, thank you, Gluon. It's accessing elements in an array. Yeah, specifically, you're going to access the elements in some kind of sequential order. And in the tree traversals, we will do the same. We're going to traverse the tree and access all the elements in some kind of pre-prescribed way. So here's what the traversal methods all entail. They all entail visiting all the nodes of the tree, just like the traversal of the array involves visiting all the elements of the array. But you know now that trees kind of have this 3-dimensional structure to them, whereas arrays could have some 2-dimensional structure. Trees, sorry, I guess we could say that trees have some kind of 2-dimensional structure, while arrays have a 1-dimensional. So with the trees, we need to choose some kind of order to traverse them in. So we could have pre-order traversal, where we start with a root and then we go left and then we go right. We could have in-order traversal, where we start with a left node, then go to a root node, and then go to a right. So that would be in-order traversal. We also have post-order traversal, where we go from left and then we go to right and then we go to root. So these are all the possibilities really that are commonly used, at least. And they're crucial for various different tree operations and algorithms that we might have. So I actually want to practice some tree traversals with all of you. And I'm going to give you an example tree. And I want you to please write the numbers that are visited in pre-order traversal. Of visited nodes. Please write the sequence of visited nodes in pre-order traversal. Okay, so I've wrote that on the bottom there. I want you all to practice because remember, pre-order traversal is root, comma, left, comma, right. Okay, so pre-order traversal is root, comma, left, comma, right. So I'm going to give you all a couple minutes to look at that. And Gluon asked for the PowerPoint of the session. So I'm going to actually make a little PowerPoint for you so you can have the file. All right. So let's take a couple minutes to practice pre-order traversal. All right. A couple of folks already giving some answer for how this would go for pre-order traversal. The answer is 1, 2, 4, 5, 3, 6, 7. So good job to both Akshat and Adel for giving that answer. And I'm going to show the solution now because with some explanation. So, think about how we'll start with the root, just like we said. So the root will be 1, and then we go to the left. So the left child of 1 is 2, and then we go to the right. So the right child of 2 is 4. I'm sorry, the left child of 2 is 4. So now we are okay to go to the right child of 2 because we've exhausted all of our left childs. And the right child of 2 is 5. Okay, so now we'll go to another right child. The right child of 1 is 3. The left child of 3 is 6. And the right child of 3 is 7. So what we're doing is we're just starting with root, and then we're going left as far as we can until we need to go right. And then we can just repeat that order when we get to 3, where we have to make another choice, and we just go left first and right second. So it's always in this order of priority. So good job, everybody, for getting that answer right. And now let's try in-order traversal. Oh, I don't want to give the answer away yet. So why don't you try in-order traversal? In-order traversal, remember, is going to be where you do left, root, and then right. All right, so we start with left, then go to root, then go to right. So try this one now. All right, everyone. Excellent work with this one. Looks like a lot of you got this. And so, yeah, we're just going to go starting way far at the left, the furthest left child. So in that pre-order traversal, we started at the absolute root, right? We said, let's prioritize root. And the root was 1. But now with in-order traversal, we're going to prioritize the leftmost node, even if it's really a child of a child. And so 4 is, really far down in terms of its level, but it's the leftmost node. So we start at 4. And then is there anything left of 4? No. So we'll do root, and we'll go up to 2. Okay, we went to root, and then we'll go to the right. So we go to 5. And then we can go back to root and go to 1. And then what's the leftmost child of 1? Well, we have 6 because it's a child of 3, and then which is itself a child of 1. So we go all the way down to 6, which is left, and then we go up to root, which is 3, and to the right child, which is 7. So that's how we would do it. And we did get one answer, which says go from 1 to 3 and then 6 and 7. But once you get to 1, remember, how would you then traverse using in-order traversal? If you're at 1 and you've already gone to 4, 2, and 5, you have to go to the leftmost node first. So you would go to 6 before you go to 3. And the reason for that is because 3 would be considered a right child of 1. So you would go to that maybe under a different one, a different type of traversal, like a pre-order traversal maybe, but not in this case. But great efforts by everybody on this one. And we're going to do one more, which is the post-order traversal. So remember, post-order traversal is where we do left, and then right, and then root. So I'll give you a minute to try that. Okay, everyone, it looks like a few of you answered the question. You all did great. I'll show you the correct answer now. So we start at 4, and we'll go, because remember, post-order traversal also starts at the leftmost root. So we go to 4, and then we go to 5, because that would be right. And then we go to root at the last. So 2 is then the root of these nodes. And then we can go up to the left once again. So we would go to 6, that's the leftmost now. And then go to the right, which would be 7, that's the rightmost. And then we go to the root. And then once we do that, we've traversed basically everything except for 1. So of course, then we're going to traverse 1 at the very end. And I did get a request for the slides, so I actually put a link to the slides from this series. It contains all the slides, not just from today, but also from the previous parts. So yeah, please feel free to take a look at that and let me know if you have any questions. Sure, no problem. So yeah, why don't we keep going now? We're going to actually do an interactive problem where we implement some of these tree rehearsals. Tree rehearsals. Yeah, we can call this a tree rehearsal of a tree traversal. So I encourage you to really code along with me, since this is our first interactive problem of the day. Think about, how you would implement these traversals on your own. But yeah, we're going to go through it together. So there's going to be ample opportunity to check it out. And the way we're going to do it is using some object-oriented programming. So we did some of this last time, but we're really going to define an object, which we'll call a node, and we'll give it some value and some left child and some right child, and then we'll build a function that can do some of these traversals. Okay, so why don't we open up our terminals? I always send this link to people in the chat because I'm not sure if you have a really good way to code, but if you don't already, this is a great website to go to. It's called Visual Studio. You can download this for your desktop. They even have a web app, I think, for Visual Studio Code. I'm not sure 100% about that, but I think there is a way to access some limited features on the web through cloud hosting and things like that. But yeah, just download that to your desktop. It'll be a great tool for you, not just for these workshops, but also in the future. But for now, I'm gonna go ahead and share my coding Scratchpad, which I have pulled up for all of us. And we are going to first start by defining a node class, all right? And we're going to define it using this dunder method, where we have init, which basically runs every time we make a new instance of the node. And so it'll have some data that we can assign. And so I'm going to make the first line of this init will be self.data equals data. So that will assign the data to an attribute of the node. So now, let's say this node has a value of 2, like the examples that I gave. Now, if you call node.data for that node, it would yield a value of 2. And then on the next line, I'm going to put self.left, and this is going to indicate the value of the left child. So I'll just leave it none for now by default, and I'll make the same for right child, because remember, with binary search, with binary trees, it's only possible to have up to 2 children. So we can just call them our left and our right children. And so I'll run this little cell now here to just define that node. And I'll make a new one, and we're going to implement what we call pre-order traversal. Okay. And so with pre-order traversal, remember the order of pre-order traversal is going to be root first, and then left, and then right. So I'm just going to write that up here. Root, left, and then right. Okay. And for those of you who didn't join the previous workshops, I do have a custom of sending along the code in the form of a code share. So you will get that code after we're finished making it together. I'll send it along to you. Okay. So let's get cooking with our pre-order traversal. Okay. So we can make a new function, def pre-order, and I'm gonna give it a root to start at, and we'll just say that if the root is defined, then we will print the root.data, right? Because we want to basically print out the values of each of these nodes. And .data is how we do that. And then I want to call pre-order again on first the left child and second the right child. All right. So this is what we call a recursive call or recursive function. And so it means that inside of the definition of the function itself, we will have a nested call of that same function, so that we'll just keep iterating over this this traversal until this condition, if root, is no longer true. And what would it mean, by the way, if root was not true? Well, that's a good question. It means that essentially there's no data associated with that. So when that were to happen, it would mean that one of these, left or right, is none. Because if you see, we're going to pass the left child and the right child both into pre-order. And if one of those is none, it means we've reached the end. So it's just going to stop the function from continuing to run. All right, that's how we basically terminate the algorithm. And now we're going to make an in-order traversal function. And remember, the order of in-order traversals is left, and then root, and then right. And so that's kind of why they call it in order, because when we visualize these trees, we usually think about having the leftmost children on the left, and then we kind of read it left to right, where some of the most lowest level roots are in the middle, and then at the right is all the rightmost children, right? So that's why we call it in order traversal. And then we can define in order traversal to be accepting root as an argument, just like we did with pre-order. So we would typically put that at the beginning there. And if the root is defined, then first we're going to call in order root.left. Then we will print the data. And then we will call the right. And the reason we do it this way is because we don't want to print right away the root. Remember, in-order traversal requires us to prioritize the left child. So that's why we put it in this order here, where we go in order recursively. Remember, this is recursive. And then we do it again for right after we've gotten back to the root. So yeah, it's really good to write recursive functions like this when we're doing tree traversal, because this function, this recursive call, will just keep iterating until we're out of left children, until the left child is none. So that is a great, neat built-in sort of feature of coding. And now we're going to do a post-order traversal where we do a left and then a right and then a root. Okay, so post-order traversal is going to be following basically a lot of the same concepts we have in pre-order and in order, but we're going to do both of our recursive function calls at the beginning, and then we're going to call the root, print the root data at the end, because for post order, the last thing we think about is the root. Okay, and so if you'll remember, when we did our example, 1 was the last value, right? So let's think about a tree now that looks really similar to what we did for our example. Okay, so here I have a tree for us to look at. I'm going to put it in Markdown. Yep, there it is. So this is essentially the same tree that we've been dealing with in our examples, our interactive questions. But we're going to now define it using the nodes that we built at the beginning. Okay, so how can we do this? Well, we're going to start by making a root, which is going to be that node 1. So this is the very base root. And then we can even, now that we've initialized a node object, it has left and right attributes that are currently none. So let's go ahead and assign to those left and right attributes? Well, we know that the left child of 1 is 2. So we can say this is 2, and the right child is 3. Okay. And then we can take this a step further. So this is level 1 here. Oh, I should change this back to Python. And then here's level 2. And now we'll do level 3. And so we'll take root.left.left, which is the left child of the left child. So we just go to the left child, go to the left child, we get to 4. And now we'll do the left child, the right child of the left child, which is root.left.right, and that's 5. And then we also want to now have the right child's left child, which is 6, and the right child's right child, which is 7. So this is the left branch. So I'll just call it the left branch, and then this is the right branch. So we do have 2 separate branches. I'll just call them that. But they are on the same level, that same level 3. So let's go ahead and run this code. And we've now constructed this tree using the root variable. Inside this root, it contains all of the structure of the tree. And we can now pass the root in as an argument to our traversals. So let's do the pre-order traversal first. And so we're going to do pre_order and then root. So if we run this code, you can see we get our pre-order traversal, just like you all did with your, I guess maybe, I don't know if you guys solved it with coding, but I think you might have solved it just by looking at the tree. But now we can verify it. And now let's do the in-order traversal. So we'll type in order and then the root. So we'll run that and we get 4, 2, 5, 1, 6, 3, 7. And now we'll finally do the post-order traversal, okay? So in this case, we just call post-order on root, and we'll get the same thing. So a little bit about this, that we're using these nodes to construct the tree, and then we can use these functions to traverse it in whichever order we please. And I'm going to paste this on CodeShare and take a mini break. If any of you have questions about the tree traversals, this would be a good time to ask it. I'm just going to quickly paste some of this code into CodeShare. All right, so I've got the CodeShare now, and I'll paste the link in the chat. So you all can go to this link. It's a new link for today's workshop. And you can download this code to do your own tree traversals. So you could build your own tree, try some traversals, and yeah, we'll learn together like that over the next few slides. But we just covered the traversal results actually, but you can just see from the different outputs, we'll see different orders, which could be useful depending on which application you're looking at. And Adol says, how are these traversal techniques helpful in the real world? That's a good question. So it could be helpful if you're searching for something and the tree has a certain structure. And we're actually going to look at something called binary search trees next, where you'll see how a tree with a particular orientation, you might search for something using concepts like traversal. So we'll talk about that in the next couple slides. So binary search, but thank you for that question. So are those traversal trees helpful? And how are some real life scenarios? So we can talk about binary search tree now for that. So a binary tree with the following properties is a binary search tree. So first, the left subtree of a node contains only nodes with keys less than the node's key. So in other words, everything to the left is going to have a value less than those roots. And then the right subtree of a node contains only nodes with keys greater than the node's key. All right, so then on the right-hand side, you would have values that are larger. And then the left and right subtrees are themselves also binary search trees. So you can think of a binary search tree as many nested ordered trees. And so let's now talk about some of the common operations you can do with binary search trees. So you can do insertion, searches, and deletion, all using binary search trees. And they're going to leverage the properties of the binary search tree, that is the ordered properties, the ordered nature of it, to make this really efficient. So you could insert data, search for things, delete things within the tree really efficiently. All right, and I'll actually talk to you now about just how efficient this is when you compare to some of these operations to some of the ones that we were looking with in terms of searching an array, right? So we'll look at the time complexity and see that the average case is log n time. So if you remember back to our merge sort algorithm, and that was an n log n algorithm. So some of those were quite intense, and we're getting a really good log n time complexity on the average case. And then in the worst case, where we have an unbalanced tree, which means that the leaves are not concentrated in a balanced way across the branches, that could be O(n) time. But regardless, if you have a balanced tree, you can have really efficient operation, similar to binary search in our arrays. And so we're going to implement some of these algorithms in our binary search tree. And so why don't we try that now? So I want you all to think about how you would implement these operations. Remember, we still have our node, which is the left and right child. How would you use that to build some insertion, search, and delete operators? Okay. I want you all to think about that a little bit. And so, yeah, we will check that. And yeah, I think we'll use that same code that we used before. And so I'll put that up. And as far as real life development scenarios, think about arrays where we actually had to have a fixed size, and if we add a new element in there, it shifts everything over. That's going to be really cumbersome. So it could be really useful if we're inserting some element of data or deleting some element, and we just don't want to necessarily alter the whole tree. We just want to alter some bit of it. But yeah, let's really dive into some of this coding here. So I'm going to just scroll down here so that we can just keep what we had before. But we're going to create a new class called a BST node. it's going to be basically exactly the same as before. You know, actually, maybe I'll just use the same node class from earlier, because again, it has a really similar structure. So I'm just going to use the same node class from before. Maybe I'll copy it from below. Yeah. But we're going to do first insertion operation, est insertion operation. So just remember that this node is specifically for our binary search trees. And so insertion, we will define insert, and we're going to take root, which is going to be that tree, that binary search tree, and then we'll take some data, which is the data that we're actually trying to insert. And if the, or actually, excuse me, I'm just going to call this node. If the node is none, meaning that that node has no value, we can return node data. All right, so we're going to create a new node here. That's the basic idea behind insertion. If, on the other hand, the data is less than node.data, this is the case where our data is smaller than the current node. So when it's smaller, we want to go to the left, because remember, everything to the left of a node in terms of the lower level branches is going to be smaller. So we're going to just keep searching down the left-hand side of the binary search tree. So we'll say node.left, and we'll call this recursive function. And I'm just going to say, note this. And else, this means that the data is bigger than the node.data. So we would type node.right and insert on the right. Okay. And so finally, we'll return the node itself. So again, this insertion function is checking to see if we're at the end of some terminal of the tree, and if we are, then it's going to return the node, a new node with some data. But if, on the other hand, we are not, then we can check to see, is the node's data, the current node that we're looking at, is it smaller or bigger than the data we're trying to insert? And so we'll just recursively, check these cases and trickle down the tree until we get to the very end when we can return the node. So that's sort of how we build the insertion function. And now we can build the search function. Or I guess I'll just name it in the same way we named the insertion operation. So we'll just call it search, and it accepts a node and also a key or a data, I guess I'll call it. And remember, if the node is none, or node.data equals data, return the node. So this is covering two cases, actually. It's covering the case where we have an empty node, and is also carrying it's also covering the case where node.data is equal to the data that we're trying to replace. Okay, and in those cases, we'll just return the node itself. And we have a question, are there any duplicates in binary search tree? And that's a good question. Let's go back to the original definition of binary search tree to find out. So remember, the left subtree of a node contains only nodes with keys less than the node's key. And the right tree contains only nodes with keys greater. So are we ever allowed to have a case where the subtree contains a node that's equal to? It doesn't say, right? It doesn't say oh, the left subtree contains nodes with keys less than or equal to. So for that reason, we could never have two duplicate values. They would all need to be unique. Right, and then Adel says we didn't really handle the case where the data I'm trying to insert exists in the BST in our insertion method definition. And yes, that's true. If the thing already exists, it would return the node because we know that the data is actually going to be equal to the node dot data. So we kind of handle it, but as you said, it's not possible to have repeated values. So yeah, it would not get really inserted, honestly, if you had two repeat values. That's a really good observation. But yeah, just looking at the definition here, we could never have a repeated value. All right, so, yeah, we'll just keep going with this a little bit. And yeah, let's go ahead and go back to our code because we have some more methods to implement. So our search method, if node.data is less than, or sorry, I want to actually say if the data is less than node.data, then we'll just keep doing our search along the left-hand side. And if else, then we have greater than. So we would go, or yeah, we would just go to the right. So that's how each of these children goes. And now we'll do the BST deletion operation where we define some function delete. We'll use node and data. And if the node is none, just like our insertion case, we just return the node. But if the data is less than the node data, we have to call the delete function again on the left child. So we just keep going in a recursive way along this case. We could check if it's bigger than node.data. And then in that case, we would go along the right side of the tree. And in the final case, where neither one is true, it would mean essentially that this is a node with only one child or maybe no child. And so then if node.left is none, we can set some temporary variable to node.right. We can clear node, so it would just be none, and then return the temporary variable. So this is, we're essentially just getting to the act of actually deleting, right? And then if node right is none, then we will set node.left to temporary, node equals none, and then we will return the temp. So that would be the case if it was if there was nothing on the right, right? And so now let's cover the case of a node with two children. So this was node with only one child or no child. So we just basically found that and deleted that. And now we can do node with two children. So as the comment suggests here, we will get the in-order successor. So we want to find the min value node. We haven't defined this function yet, but essentially we're going to find the successor node by calling it on the right, because the right contains all of the values larger than the current one. And we will delete, call delete again. And return node. And remember, I told you I was going to define min value node. So we'll do that now. And so we'll just call it current equals node. And we're going to check while current left is not none. So that means we're going further to the left, down the left children. We'll just keep updating the value of current. And eventually we'll get to that leftmost child in this branch of the tree. And that would be the successor node. So it'll bring us to that min value node along the right child branch. So it's just that next largest node. And eventually we will return the node that gets deleted. All right, so that's how this works. And we will now run this. I'll just run the stuff. And remember, we have our in-order traversal already. We can print this stuff out. So it's time to test the BST operations. Okay, so I'm going to set root equals none, and I'm going to set some data, which is going to be 50, 30, 20, 40, 70, 60, 80. Sure, why not? And we'll say for each item in the data, we're going to call insert to insert these values into the root, okay? So let's see what happens then if we, after we're done with that, we can call an in-order traversal on this root to traverse the tree. Okay, so by implementing it this way, we can put the traversal items in order. And let's say we wanted to now search for a key. So let's say we want to search for 40. So we would say result equals search, and we just pass in our root, and we pass in 40. So remember, the search algorithm is going to look through the nodes. If we found it, we'll just return it. If not, then we will check the left node, the left branch and the right branch recursively until we find it. In the same way that we did binary search, where we looked at the greater half or the smaller half by comparing to that midpoint. So let's run search. Oh, I never actually printed out the result, so let's actually print out the result. So it returns the node. So it did find it did find the result essentially. So here's the node. And remember, our nodes have properties. We can do .data on our node to check that it's 40. All right. And so why don't we now try deletion? So we'll say, let's delete 20 from the root and update the root. And we'll do another in-order traversal. So if we do this, remember our delete method should be able to remove a node. So it's similar to search in the beginning, where we're basically implementing search again. But once we find the node, right, we'll have a case where it might have one child or no child, in which case we need to kind of restructure things based on one child or no child. And with two children, then we're going to find that min value node, which is the next largest node that's going to be the successor. to reconnect them before we delete, right? So why don't we check delete and see if it worked? And it looks like it did. So we did delete 20 from the tree. Okay. So yeah, the most complicated thing about this, I think, is the restructuring of the tree. But I encourage you to follow the logic here, on your own. Try to actually trace what's happening in the delete, because you do need to restructure the tree because it's similar to a linked list. Yeah. Okay, so Adel says, I'm sorry, I'm climbing. I don't get how it is handled in the insertion. So yeah, so it didn't get added to the right of the node, I don't think. But maybe it's implemented wrong. Let me check the insertion here. So let's go back and look at insertion. First, we checked if the node is none. And if that was the case, we returned node data. If the node is to the left of node.data, this is the case where the node we're looking at currently has some value. That means we want to go over to the left. So we would just traverse to the left. So in this case, we'll start at the root. So the root, if you remember, of this tree would be, well, let's try this. So root.data is 50. So when we insert 50, we're inserting that at the root. And then 30 would go, when we do root.left.data, 30 would go to the left because 30 is smaller than 50. And then root.right.data, we could see, is 40 because it's larger than 30. Oh, I see what you're asking now. What will happen to the repeated value to the right of the node? So let's try this. We'll add 20 twice. Yeah, so it adds it, right? It doesn't add it, but now this is no longer binary search tree. So we can't make a binary search tree with repeated values. Remember that from our definition. So as it's currently set up, it's a binary search tree. All right, so let's keep going then. But yeah, if you want to handle that, you can handle that in the insertion function by searching for whether the node already exists, and if it doesn't, then you just quit out of the insertion, right? So if we wanted to, we could handle that. So why don't we try that? We just go through and we just say search node data, and we say if this is not true. So this would be if we just don't find it, right? Because that would, then we would just have return some error. Right. So let's see how search would handle if we did like 45. Oh, so it actually just throws an error. So we could just say, we could just try to search for it at the beginning. Let's try search. We could just say error, BST cannot have duplicate values. So this would be a good way to handle that. And if we then passed it some sort of array like this, oh, I guess we need to update everything. I guess it didn't quite work that way. It should work though, I'm not sure why. Oh, probably because I'm redefining the root every time. Well, if anyone wants to try to implement that exception, definitely take a whack at it. But yeah, by the definition of BST, you should not have a duplicate value. All right, so BST operations are efficient when the tree is balanced. So you can understand now that recursion is essential to implement these tree operations. Okay, and we can now talk about what happens when a BST becomes unbalanced. So it is possible to have an unbalanced tree, but it degrades the performance to ON. And that's why we always want a balanced tree. So there are examples of trees. One is called AVL tree, one is called red-black tree. These trees use rotation and rebalancing techniques after they do an insertion or a deletion, so that we are not always adding to one branch of the tree and making it really lopsided, right? That would not be good for the speed of the algorithm. So yeah, let's continue on to I have heaps and priority queues next, but we'll just take a quick 2-minute break before we get there. All right, so now let's move on to our heaps and priority queues. This is another advanced concept here. So let's dive right in. It's basically a specialized tree-based data structure that satisfies the heap property. And so there are two properties here. First is called max heap, which for any given node, the key of the node is greater than or equal to the keys of its children. And there's also min heap. So in a min heap property, we would have the key of the node being less than or equal to the keys of its children. So when we have a heap, it's typically being implemented as a complete binary tree. And you might remember from our complete binary trees that those are going to have a special property where each child is completely filled, or each level, excuse me, is completely filled, except for possibly the last level. All right, so that would be a heap. And so min heap is like this left case. So min heap is where each parent node is less than or equal to its children. You can see that the highest values are on the lowest level here. You have 14, 16, and 18. Those are all smaller than their second level neighbors, 7 and 11, and then 5. is the smallest and is at the root. So that would be an example of min heap structure. And then here's an example of max heap structure. So you have a case where each parent node is greater than or equal to its children. So you can tell that at the bottom we have 10, 14, and 11. And then on the next nodes, we have 16 and 18, which are both larger. And then finally 20 at the top, which is the parent node. So that's going to be the greatest in the max heap structure. So these are really useful for things like priority queue. So let's say you have a lot of tasks and you want to figure out which one has priority. Max heap is a really useful way to do that. And so you'll execute that highest priority thing first at the root of the tree. And you could also use it to find some sorting. So there's actually an algorithm called heap sort, where you will use max heap to sort. So that can be really useful. And those same things, you could use min heap for the same type of thing. But yeah, so here's a little bit about priority queues. And it's an abstract data type where each element has a priority, and they will serve the function based on priority. So let's say you have a really high priority task, but it was not the most recently inserted, it will still get served first. And so that's a little bit different than the first in, first out, or last in, first out principles that we had in part 2, where we looked at some of the stacks and queues. And there's some common operations that we can look at, like insert, which adds an item to the queue. There's also extract min, which will remove and return the item with the lowest priority. So we'll usually use min heap for that. And then decrease key is where you decrease the value of a key. And that's used in algorithms like Dijkstra's algorithm. I don't know if any of you have ever looked at that one, but that's a really cool algorithm for, it's like traveling sales algorithm. I don't know if you ever looked at that, but yeah, we are gonna look at an interactive problem for implementing a min heap. So under the problem statement, we'll create a graph using an adjacency list and implement basic traversal methods. So let's dive deep into our codes to get this off the ground. All right, so let me actually put some of this BST stuff in the code share so that you all can see. I never put it in the code share, I just realized. Yeah, it's really important because, you want to be able to recreate a lot of these codes. And if you want to try what Adel was suggesting, that would be really cool to see if you can get it to reject an insertion of a duplicate value. But all right, now it's all added in. So we'll make a new code here, and we're going to use a list to represent the heap. And we're going to define a couple methods for insert and extract min specifically. So we're actually going to do a min heap example. So let's start by just making a new class, because remember, now we're not really dealing with binary search tree. We're dealing with min heap, which is a more special case. So when we initialize the min heap, we're going to start it out with an attribute, self.heap, which has an empty list, okay? And then we can make a parent function, which gives self and I, and return I minus 1 divided by 2. And then we will insert a new key. So we'll have a function to insert a new key. And so it takes in the argument self and the argument key. Remember, self is the heap itself, and then key could just be whatever you're trying to insert there. So we will populate that now. Sorry about that. I got a little bit disoriented there in my typing. Self.heap.append key. And we'll set the I equal to length self.heap minus 1. And why are we doing this with the I? You know, you might be wondering, what's going on with I here? Well, I is telling us, in a sense, the location of where we are. So the parent is going to be based on, in a min heap, this value. And then here we are looking at the maximum I, the maximum index. So that is why we're doing it. And so now we can keep going. We're gonna now fix the min heap property if it's violated. So we'll say fix the min heap property if it's violated. Okay, so in this case, we're going to say while I is not equal to 0 and self.heap, self.parent, I is greater than self.heap, I, will swap with the parent. So this looks really familiar to some of you who might have done some of the sorting algorithms from before. So we're essentially asking these two elements to swap. Because remember, we can never have in our min heap a case where the parent is larger than the child. So that's exactly what we're protecting against here. And of course, if we're at the very top, then we don't need to do this because, you know, that will just automatically satisfy it. And then we'll set I equal to the self-parent I. So we're going to put the key right in there. And then here, as the comment says, what we're going to do next is decrease the value of key at index I to new val. So we're basically going to do what we call heapify. Any of you heard that term before? What is heapify? Basically, heapify is a process that you use to maintain the heap property of the structure. So we're going to use, in this case, heapify down, which is what we do for keeping min heap valid. So let's go ahead and heapify down. And we'll say smallest equals I. And we'll say left is 2 times I plus 1. And right is 2 times I plus 2. So these will be our left and right branches here. And then n is the length of self.heap. And we can check if the left is smaller than n and self.heap of, I guess we could say, left is less than self.heap of the smallest, which remember this is I, then we'll set smallest to be equal to left. So this is the case where we're trying to heapify down, so-called. And we're going to heapify down the left. Move the priority down the left branch. And then we can do the same for the right branch. And we would just say smallest equals right. And if the smallest is not equal to I, meaning that we're not, we haven't reached this, then we're just going to swap and continue heapify. So we'll implement this swap here, where we swap I with the smallest. And then we will just do our min heapify again. And remember, this is a recursive call. So we're checking every possible branch to try and place and try to heapify down and basically place all of the elements where they need to be. And so when we remove a node or replace one, we need to move everything else down in order to restore the heap property. Okay. So you would need this also for inserting an element, and so for either case, that's what you would need heapify for. All right. So yep, that pretty much sums it up for heapify. And now we're going to do extract min. Remember, I said extract min is one of those that we need for a crucial heap property. So extract the minimum element, and we'll just call it extract min, and just give it some self that it passes in some heap object, some min heap object. And to do this, we're going to say if the length of the heap is 0, then of course we would just return none. But if not, we would move the last element to the root and just heapify. So move the last element to the root and then heapify. Heapify down. So we'll say root equals self.heap 0. So that's that first element. And then we will say the last item is going to be the pop of this. So remember, when you pop from a list, you're getting the last item. And we're actually removing that then. And then we'll just check if the heap still has elements in it. And if it does, after that pop, then we'll just set the first element equal to the last item. And we'll do it again. Okay, so that's how we do the heap, and then or the extracting of the minimum, and then we'll just return the root at the end. All right, and then we will, I suspect the tabbing is a little bit off here. I guess we'll have to fix that. Maybe I'll fix that right now, actually. I'm not sure how that happened, but everything got off by 1 tab. There we go. That looks a little bit better, I think. Okay, so now we're going to implement a display heap. So we'll just call it display, and we'll just say print self.heap. Okay, and so now this is our code for the heap. It's a lot of code, really, and so maybe we can try an example. All right, so I'm just going to make an example min heap using our new object. And we'll just say that it has some keys. All right, remember that we can put keys into here. And so we say for each key in keys, we will just insert that into the min heap. And why don't we also then just display at the end so that we can see what it looks like. All right, so here's the min heap, how it looks. And remember, we will have it will float the lowest root up to the minimum case. And we can extract the minimum, actually. We expect this to give us 2. Or excuse me, expected to give us 45. And then we can just display that again. So now there's no longer 45 there. All right. So that's sort of how the min heap works. And so the graph representation would show each node and its adjacent nodes. So this is a next thing to talk about, graph traversal algorithms. And there's things like depth first search, which explores as far as possible along each branch before backtracking. So you could use that type of algorithm to detect cycles, do sorting, solving puzzles with only one solution path. There's also breadth first search. We talked a little bit about breadth first search actually at the beginning of part 2, but this is where you're exploring all the neighbors at the present depth, and then you move on to the next one. This is really great for social networking sites, web crawling, things like that it's used for. And so we're going to now do an implementation of depth first search. And so let's actually look at some live case here. So we just did heap. Now we're going to do a graph class. And we'll do some initial init method. And for the graph, we're going to use curly braces. So that indicates a dictionary object that we can assign some kind of key value pair. Although yes, we may have to actually save the graph for next time, because I noticed now we're running a little bit low on time, and I want to get to one last topic. So maybe we will save this for next time. I'm just realizing that we might not have enough time to do graphs. I don't want to rush it either. So maybe we'll go to our interview strategies and tips, which is the last part of the data structures and algorithms practice that I wanted to do. So we'll talk about graphs later, but I wanted to make sure I covered this before we finish today, and we only have about 15 minutes left. So you know, when you're approaching these types of problems, there's a lot of things you want to I encourage you to think about. So first, make sure that you understand the problem that you're looking at. So this is something that, you know, for example, Adele, when you said about, you know, can there be repeated values in a binary search tree? That could be a clarifying question that you really want to mention. And then planning before coding. So this is where you discuss possible approaches. For example, you remember when we did our pre-order traversal, our post-order traversal, and our in-order traversal, we discussed how this looks visually before we implemented it in code. All right. And we also want to make sure that we communicate clearly. So that's also part of this examples of traversals that we did, and explaining your thought process behind it. Why do we use this I, for example, in the min heap? Well, I is to show the index of where we're inserting our new node, for example. And we'll want to make sure to write clean code. So that's involved with, you know, making the most modularized code possible, as we talked about in the Crack the Technical Interview workshop. and test and optimize. So consider some of these edge cases, consider some of these potential optimizations that we can do. And there are some common mistakes that people will do sometimes, like rushing into a code without a plan. That's an easy way to get lost. And you can ignore some edge case or validation for your inputs and not explaining your reasoning as you go along. So while you're doing some of these, make sure you explain them to the person who you're looking through, who's giving the interview. And now I want to talk a little bit about algorithmic problem-solving strategies, because someone mentioned they wanted to talk a little bit about dynamic programming. And so we now have some time to do that. And we'll maybe go back to graphs and Dijkstra's algorithms another time. So here's one really common algorithmic strategy called dynamic programming. It's a method for solving complex problems. You break them down into simpler subproblems, and it's really useful when your problem exhibits some optimal substructure or overlapping subproblems and things like that. And so there's two key concepts I wanted to mention here. There's memoization, which is the top-down approach, where you're going to store the results of the subproblems as you go along so that you avoid redundant computations. And then there's tabulation, where we have the bottom-up approach, where you're going to build up the solutions composed of the smallest subproblems. So that would be the bottom-up approach. And we're going to solve this interactive problem, which I call the 0-1 knapsack problem. And this is a problem that we can apply dynamic programming to. So given the weights and values of n items, so you have n items that each have a value and a weight. So they could have a weight of 2, a value of 3, for example. Put the items in a knapsack of capacity W, so that's the total weight capacity of the knapsack, to get the maximum total value in the knapsack. So we are optimizing the value, but we have the constraint of the weight. So the weight has a maximum of 5, and the maximum value is 7 in this case that we have in this example, which would be putting items 1 and 2 into the knapsack. So we call it 0-1 because you cannot ever break an item. You have to either pick it up and put it in the knapsack or don't pick it. So this is kind of a complex problem, right? And we need to optimize, but we have a constraint. So let's try to solve this knapsack problem. And we're gonna leave the graphs to it for another time. I don't want to get too in the weeds some of those. I feel like we did enough of them, but let's go to the knapsack. So we're going to define a new function where we'll have some weights, some values, and some capacity W. Okay, and the first thing we're going to do is type the length of the weights, or I'll actually hit the values. I'm not sure. It really doesn't make a difference, but the first thing we're going to do is initialize the DP table. Okay, so we'll say DP equals, and we're going to do a loop of 0 for x in range W plus 1, for x in range N plus 1. So what does this mean, right? This is kind of strange. Let's actually look at the DP table if we were to just build that and nothing else. Oh, we can't. That's right. Let's define the variables. So we'll just say weights, values. W is 1, 2, 3, 3, 4, 5, 6. right, so the DP table is going to allow us to consider different possibilities for values and weights, and what we could possibly include, possibly exclude. You'll notice that the rows are defined by the W plus 1 and N plus 1. So you're going to basically have all the possible combinations, right? Yeah. Oh, sorry about that. I forgot to put the length of the values here. So it does look a little bit different. There we go. So the rows are defined by all of the possible n's, so all the possible values, and then the columns are defined by W. So we're going to have different possibilities for weight. And so the dynamic programming table, we can build the table in a bottom-up manner. And remember, bottom-up manner is where we're going to be building up the solution from the smallest subproblems. So we're going to actually look at some of these possibilities for the dynamic programming. So let's loop through all the possible values. Remember, we go through range n plus 1. And we'll say W is the range of W plus 1. So all the possible capacities here, weights. And if I equals 0 or W equals 0, then in that circumstance, we're just going to apply 0, keep the element in the dynamic DP table equal to 0. But if it's true that the weights is less than or equal to W, so this is the case where we're allowed to include the item because the capacity is not yet reached. We can include it. So we'll include the item in our knapsack. And that will mean that at I, which is, remember, the value, and at W, which is the weight, we will do the maximum of the value plus the previous I1 at the W minus weights I minus 1. And I minus 1 W. So we're going to reassign this value to the maximum of these two possibilities. So remember, this is the value added to the current value of the knapsack or the previous case. So we will maximize, and if not, then we have to exclude the item. Because that means that including the item would actually completely take us over the limit. So at the very end of this for loop, when all is said and done, we'll return the DP entry at N and W at the very end. So we're essentially solving each of these problems. You can see we're actually getting the value, checking to make sure that it doesn't put us over the weight limit, and add that to the previous calculation in the DP table. So that's why it's called bottom up, because you're basically going to build up the solution from these subproblems where you're incrementally adding to the knapsack. All right. So we can check this out, try it out a little bit ourselves, whether it works or not. And yeah, let's try it. So we can scroll down, do some weights, some values, and some capacity, which is capital W. And so we want to get the optimal solution from knapsack So we should run this, and it gives us 8. So that's telling us that 8, this single item was the optimal solution, because it brings us all the way up to the capacity of 5. And we just grab that and throw it in the knapsack. And let's actually add a print statement here to print out DP so we can see what DP looks like. Yeah, you know, actually, maybe I'll just return DP, because I think I'd rather see it as a multi-dimensional array. So yeah, on the rows, these are the different possible values. And on the columns, these are the different possible weights. So each pathway represents a possibility. So you could have placed in this 3. But once you place in the 3, you're pretty much not able to get to 8. In this case, you go from 3 to 4 to 7. In this case, you have 3, 4, 5, 7. In this case, you have 3, 4, 5, 8. So at the very last part, we arrive at the optimal solution. So that's a little bit of an introduction to dynamic programming. And I'll give you another problem, which is also in this presentation, Sudoku solver. So implement a Sudoku solver that fills the empty cells of a 9x9 Sudoku grid. And I'll give that to you as an example exercise to try on your own for next time. But yeah, that concludes our workshop today, because we can't go over the time. But hopefully you all enjoyed doing a little bit of more advanced work with algorithms. We did some heap problems. We did implementation of min heap. We did some binary search trees and tree traversals. So hopefully that was kind of an interesting foray into some of these more. And we will have next times. Yes, so I think there will be some more exploration of these topics in a future Global Hack Week. So just stay tuned for some of these, and we'll do some more fun problems. But yeah, thanks everyone, and hope you had a great day.